uh, Sweet. Get to bring it home with a good acid talk. So yeah, this last topic for me tonight, at least, is I'm hoping is going to sort of bring together a few details from the earlier bit, and maybe even touch on a little bit about that last talk as far as some of the what was it called when you're not in Mediocristan? Extremistan? Yeah, the Extremistan. Maybe we can touch just a little bit on Extremistan. So this is also going to be more work kind of left over from my dissertation, and it was about studying the effects of sulfuric acid on ice and how it changes its mechanical properties and its microstructural evolution. So back to this question that I started out with, what is snow? We already decided, or at least I told you what I think, is that we think of it as white, cold, and reflective, but it can be, hot and black, just depending on how you think about it from the materials perspective. And so to take that one step further and apply that to ice, another way to think about snow, or the way I think about snow, is that it's just ice. It's ice with lots of air in it, lots of pore space, right? So it actually, to me, is just the more complicated version of ice. The other places we encounter ice are in our glaciers, our ice sheets, in our cocktails, whatever. We encounter ice everywhere in different forms. And from the material science perspective, a way that we can think about this is with a phase diagram. And we can compare thinking about ice as a material to other common materials, like iron, for instance. So what you see here is that given a certain temperature and pressure, we can have ice in its solid form is the way we think about it, or it's just H2O, right? So we can have solid, liquid, or vapor depending on temperature and pressure. And the same thing for something like iron. Depending on the temperature and the pressure, you can have a solid down here, a liquid, or a vapor form of iron. And this goes back to that, snow and ice is thermodynamically a hot material. So if there are steel beams holding up this building, we're not anywhere near their melting point, so we're not worried about them starting to sag and to bend and give way structurally, right? But for ice everywhere in our world exists near its melting point. So it's always changing. It's always trying to move a little bit if there's any kind of stress or load on it. And so when you think about this as an analogy to other materials, you think about, well, how would you bend a piece of iron? You'd heat it up, get it close to its melting point, wail on it with a hammer, or just, if it gets really hot, it'll just start to viscously flow, and it bends, just like a blacksmith does. We've seen this everywhere around us in nature. We see how snow comes down off a rooftop, let's say it's under some load, it's under the load of gravity, and it starts to bend, just the same way. And the molecules are rearranging themselves and allowing this to happen because it's thermodynamically hot. Okay, so what else is like ice, sticking with iron and iron alloys? One way to look at ice in a really quick and dirty way in the lab is to cut a thin section of it and look at it between crossed polarizing filters. So essentially taking each lens out of your sunglasses and crossing them with each other and putting the ice in between it. You should try this sometime in the field. And you can see sometimes the structure of the ice. So these are all individual grains, as you would call them. So this is just like snow grains have all been bonded together, making a solid, which is ice. So if you just start plucking out one or more of these grains, you start to get closer and closer to what we think of as snow, right? So that's how I like to think about it. So I like to play games when I give talks like this. So one of these is an iron alloy, and one of these is ice, just to further draw the analogy here to ice and snow just being like any other material that we study with similar properties. Who says the left is iron? I have one for the left being iron. Who says the right is iron? Oh, a few more for that. All right, well, actually, this is the iron alloy on the left, and this is just a piece of ice, polycrystalline piece of ice on the right. So you can't really tell, and that's because these are very similar systems. The ice doesn't behave that much differently from metals and alloys, as it turns out. And also, rocks and minerals behave and can look very similar to ice. So the things we've learned over the centuries and certainly the decades about how metals and alloys behave, we can learn from that. We can apply that directly to our ice case, and then because snow is just a porous version of ice, our snow case. And that's kind of the approach I'm taking in this research in this talk here. Okay, what other materials are like ice? So here is a scanning electron microscope image of, again, a flat piece of ice. I think I showed this one earlier, actually. You see the grain boundaries here are the dead giveaway for what you're looking at as polycrystalline. Anyone want to take a guess at what this is? It's a giraffe. Not relevant really at all to this talk. I just find it fascinating that giraffes are covered in grain boundaries. Really fascinated by this. And maybe we should study that, but maybe we can talk more about that later after the session tonight. Okay, so moving back towards the research. So this is just kind of setting you up for thinking about this as a material, thinking about ice as a material. The question for this research was, what are the effects of sulfuric acid on the mechanical properties of ice? And the reason we're looking at this is because sulfuric acid, in case you didn't know, is naturally produced in the Earth's atmosphere. And it finds its way into our rain and our snow, which means it's in our ice sheets and our glaciers, it's in our rivers and our streams. There's trace amounts of sulfuric acid naturally produced from the output from volcanoes, biomass burning, other mechanisms as well. It gets naturally converted in the atmosphere to sulfuric acid. It snows, it makes its way into our snowpack. And then hence into our ice sheets as well. So one of the questions for me in this was, how does this affect the flow rates of ice sheets and glaciers? And one of the things I want to get you to think about here is, how could this also be extended to applying to our snowpacks? So to test this in the laboratory, we make samples of pure ice, polycrystalline ice in the laboratory, dope it with sulfuric acid, trace amounts, and then try and do all your typical engineering tests to it. You know, we stretch it, we compress it, we plot stress and strain and see how it behaves and whether or not it behaves any differently. So this is a cylindrical piece of ice that we're going to put under compression. This is a dog bone shaped piece of ice that we're going to pull on. To give you some scale here, these are like the size of a beer can or something like that. This is how we make them with this little setup over here. This is another picture of a piece of ice placed between two cross-polarized filters. So again, you can do this with your sunglasses if you can cut your piece of ice really thin. And these different colors all correspond to the crystallographic direction of the ice grains pointing off into a different direction. That's not really too important for this talk tonight, but just so you know, that's what the colors are. So what we did was take the cylindrical pieces of ice and put them under compression and brought them to 5% strain. So we compressed them by 5% of what their original length was, and did that at different strain rates. So as fast as a minute, for 5% strain, and as long as like 13 or 14 hours to get to there. And this is showing what it looks like if you do it really fast, so like a minute or so. You get lots of cracks in the ice, but it doesn't just fall apart. It still has some structural rigidity to it. And then also over here, we made this jig where we would stretch. We would put weights, you can see weights hanging down here on these dog bone pieces, and we let that weight sit there at a constant temperature for sometimes weeks, like up to 8-9 weeks or so. And we'd see how the ice actually stretched over time. And then, of course, one of these samples would be doped with sulfuric acid, like 10 parts per million, so just a very tiny amount. And then one would be just pure water, so to serve as our control in our comparison. And so what we'll look at is how those two compared to one another. In addition to the mechanical properties, I wanted to look at how does the microstructure change. So if we take this sample after testing, we look at it with micro CT, with a scanning electron microscope, with cross-polarized light imaging. It's all kind of shown over here. So just these different characterization techniques. And for the dog bone shaped specimens, we would do similar. We would do the cross-polarized light. We also did Raman spectroscopy. I'll talk more about that in a minute. And also looked at it in the electron microscope. And so here's an untested sample, 0% strain. And this is what a sample looks like after it's been stretched, 40%. So this is pretty incredible. It's a solid piece of ice that if you let it sit at a high enough temperature and with just a high enough load, and for a significant amount of time, you get it to viscously stretch. And there's something that I said there that is really important to this talk, and something, if you don't take anything else away, I want you to remember this. What we're talking about here is what's called creep behavior, where you have this really slow, viscous, elastic kind of, or not elastic, just viscous flow of a material, like you see here, stretched out And it's very much time and temperature dependent. So the higher the temperature, the easier this is to have happen. The longer time that goes by, the more likely you're going to see this behavior. The load doesn't have to be that high. Okay, so you think about when you bend your paper clip, you're taking that paper clip to its yield point, and you're yielding it, is be like the engineering term, I guess. But even if you just barely pulled on it at all, if you let it go long enough, you'll eventually bend it, and it'll never reach that high stress. But just these low stresses can be really important if it's thermodynamically hot material, and you let it sit there for long enough, which is what we did with these. So just jumping to some of the results here. These are the results from the compression tests at 5 different strain rates. So I told you sometimes it'd be 1 hour to 5% some strain, sometimes it'd be 13 hours to 5% strain. So what you see initially as you put on the load is that the solid line here is the pure water samples, and the dashed lines are the ones that have been doped with sulfuric acid. And what you see is a difference in the peak strength. So this peak is higher than this one. So the sulfuric, just that little bit of sulfuric acid added actually made the ice weaker, to the point. And we saw that consistently at all these different strain rates, even though they started to come together a little bit more down here. And that's more related to, some fractured more than others. So in general, just a little bit of sulfuric acid in the ice weakened it. We also saw differences in the microstructure. So here we saw, for instance, larger grains that came out at the end of the test than over here. That was something that we saw in all of our samples. And we also were able to do some micro CT analysis on these compression tested samples to see how many cracks had formed, or where the cracks had formed in the ice. I don't know why this always messes up. So the black here are the cracks in the ice, and the clear is just the ice. So we're able to see these crack networks. We also were able to look at these under a microscope and see how the cracks kind of linked up and where they broke, which was always at the grain boundaries, right? Which is kind of what you'd expect. That's going to be the weakest point for these cracks to occur. And we saw differences, which was interesting. So the sulfuric acid doped ice, if you want to see it on the plot, it's here. If you want to look at it in the pictures, it's here. The sulfuric acid doped ice had more cracks than the doped ice, or than the pure ice. And you saw that at all the different strain rates at different temperatures, and the cracking started sooner. So the sulfuric acid seemed to make the ice weaker in compression, and also for the cracks that we did occur, it made it so that the ice was more easily able to start cracking.
Hey Kevin,
yeah.
What's the scale roughly on the photos?
These are probably 1.5 inches or so in diameter.
That big, okay.
Yeah. And these are micro CT images. All right, so that's sort of the short result for the compression tested samples. If we look at the tension tested, so the creep tested specimens of ice, what you see is that the sulfuric acid here in black had, this is time down here and the strain up here, and we're letting it go for, in these tests, up to around 2 weeks. We saw that the sulfuric acid doped ice seemed to strain faster. So there's no cracking happening in these samples, all right? It's just stretching. And it stretched faster than the pure ice with just, I'm going to say this again, 10 parts per million of sulfuric acid added to the ice. So it's just trace amounts, just like it happens in nature. So this was a pretty interesting result, too, that we saw this in this kind of different form or different type of behavior. And again, we saw even more extreme results in the differences. So if we look at the undoped ice, pure ice over here, and compare it to the sulfuric acid doped ice at 10% strain, these grains are, a factor of 2 or 3 larger. So something very different was happening just because of the sulfuric acid being added. And the last interesting thing that I'll point out, we used Raman spectroscopy, which Raman spectroscopy is essentially shining a laser on a material, and that laser causes the atoms in that material to start vibrating, and then however much vibration you get, that's energy. So whatever you're measuring of the laser on the other side that difference between the energy that was lost due to the vibrations of the material tells you what the material was, and also what kind of bonds that were present. Point being, if you look at water, you can see the difference between solid water or ice here as one peak and liquid water over here as a totally different peak. So you can see the difference between liquid water and solid ice using Raman spectroscopy, as well as the presence of things like sulfates, so you can see sulfuric acid as well. And that was an interesting result because here we looked at, so again, this is just a piece of ice. You see the grain boundaries, and we call these triple junctions, where you get the 3 different grains that come together at one point. And that's a common place to look for, where the aggregate of sulfuric acid or any other impurities might end up. So we looked there. And in this sample, what we saw was that you have a peak here for the sulfate, so there's sulfuric acid here and here and here. But we saw predominantly an ice peak with some influence of liquid, but not pure liquid. So mostly ice there. So enhanced liquid peak. But in this sample, what we saw was sulfuric acid in these different places, which is shown by this peak here. And we saw 2 that were mostly ice with some liquid, but 1 that was just pure liquid, so right here. So this was I don't know, for me, I spent many hours in the lab looking for this, and I was pretty happy to have finally found it a couple times. But what it says is that even though you have this solid piece of ice, you're below freezing, all that sort of stuff, if you get enough of a sulfuric acid concentration in the right places, you can actually get a liquid to form there. So you're holding a solid piece of ice in your hand, but there can be liquid inside. And what does that mean for the mechanical properties? I think that helps to explain some of the difference in why the ice became weaker, because now it's able to sort of think of all the grain boundaries being sort of lubed up, so to speak, right? So they can kind of slide past each other a little bit more easier because you have some liquid that's in there. So that kind of made sense and helped to explain some of our results. So in conclusion, okay, these are the conclusions just for the ice. We found that the sulfuric acid decreased the viscosity of the ice, increased the mean grain diameter, induced an earlier onset of microcracking, becomes concentrated at the grain boundaries and triple junctions, such that we'd see these liquid-like phases. So what does this all mean, right? I know that's what I see, that look on everyone's face right now. It's like, awesome. So what does this mean? All right, so this is where I want to kind of go back into the snow world that we all kind of work in and live in and think about this, right? So sulfuric acid is naturally produced in the atmosphere. It's in all of our snowpacks. It's out there right now on the hill. What are the effects that it could be having on the mechanical properties of snow that we haven't even started to investigate or really even to think about? So for any avalanche, we need to have failure in multiple places, right? The crown, the flanks, the bed surface, the stock wall. So we need failure in tension, compression, shear. This is from McClung and Shear. You guys have all seen this. And so you need basically these bonds to break everywhere for this failure to happen. Where do the bonds break? They break at the grain boundaries where the snow grains come together. And what I just showed you was some data that would suggest that if you have sulfuric acid in the ice or the snow, given that snow is just ice with a lot of air in it, that it can maybe break easier there or break sooner there. So some things that started to go through my mind when I think about applying this work to snow. Also, if you look at some previous work from Chin and Baker 2010, if you look at the way that ice grains center together, this is looking at a time series where you have just a little bit of a bond here, and then over time you grow more of a bond between these 2 ice grains. If you look at it with a scanning electron microscope, this is also from their work, you see that it's really this network of fingers kind of growing between these 2 ice spheres in this example. And if you look at the picture version of this grain boundary isn't just going to stay in the one place. It can also move. That's something that we kind of illustrated earlier with the grain sizes or the being different between the sulfuric acid doped and the undoped ice. So this thing can move. Okay, so I'm going to try and put this together. So if you're looking at this, you're thinking about the way that ice can viscously flow. Like I took this dog bone sample and I just stretched it. I put this low load on it over a long period of time. As you're stretching it, so like this guy right here, as you're stretching it, you're getting mass is conserved throughout this sample, right? So you're getting this decrease in the cross-sectional area here, and the cross-sectional area is directly related to the level of the stress. So you're seeing more stress be added to that one spot. It reminds me of this a little bit, right? So you have a slab of snow out on the hillside. It's got the force of gravity acting on it. So there's your very low, let's say, load applied. It's always near its melting point. So you have a high temperature, thermodynamically it's hot. And it sits there all winter long. So you've got the time element. So you've got everything you need actually for some sort of creep deformation to be happening. And at what scale? Are we talking slope scale, the whole thing is moving? Or are we talking the bond scale? To where is it possible that these bonds in between grains at the interface between, say, two different snow slabs are being just slowly pulled and stretched so that the stress is increasing? These are the things that I'm thinking about with how could this be happening without the sulfuric acid? But when you start throwing that in there, it makes you think about how it could be kind of instigating these different processes. And so what I think about mostly for this is I've been struck a couple times at different workshops I've been at listening to people talk about post-control avalanche release or surprise avalanches, the ones that truly catch you off guard. Are those completely unexplainable, or is there just something happening at a scale that we're not used to looking at or thinking about? Not to mention, sulfuric acid is only one example of things that are in our snowpack. There's lots of other things out there too. What are their effects? We haven't really tackled that yet. So these are the same conclusions I listed before, but the ones I'm thinking about now, and the ones I'd like for you to think about, is your kind of takeaway from this little talk is what about time and temperature dependency for snow stability? The snowpack's always changing. It's a very dynamic material. It's always near its melting point. It always has this low stress applied to it. How could that be changing over time? How do individual snow grains creep? All right, so like at those bonds, how are they being pulled? How are they stretching? Are those stresses going up over time? Can that not explain or at least hint towards these extremistan events, if you will? And what does this mean for the failure at the grain boundaries? So for any avalanche to occur, we have to have failure. We have to have a crack. We have to have propagation. We have to have bonds break. How does that happen in the natural sense, in the triggered sense, and then in the sort of long-term post-control sense, I guess, is what I'm thinking about. So those are just my thoughts. I have no research to back up all this snow talk that I just kind of spewed out to you, but it's the direction I would like to go in the future, and I'd be happy to hear your thoughts and answer any questions if I can. So thank you.